Welcome back, Engine Performance Expo viewers. Unfortunately, you probably already know who I am, and you probably know who this guy is too. Keith Jones.
Hi, everybody.
Lake Speed Jr. We're here at Total Seal today to talk to you about two terms that, Keith, sometimes get kind of confused.
Yeah, they certainly do.
So, crosshatch angle and surface finish, they're not the same thing.
Two unrelated subjects.
So let's define what is crosshatch angle.
Well, crosshatch angle is pretty much simply that term, the angle of the crosshatch.
Yep.
So we've heard the words 45-degree crosshatch angle, very common number, but what some people don't understand or know is that is what is known as the included angle. That is, if we draw, here's your two crosshatch cuts, if we draw an imaginary line through the middle, we're 22.5 going up, 22.5 going down. That's our 45-degree crosshatch angle. Or, if you measure it simply off the top surface, the deck, you'd be coming down 22.5 degrees.
Right.
That's how you define your crosshatch angle.
So if you're 45 off the deck, you're actually 90.
You're actually 90.
Yeah, so that's where it's really important to know these definitions of what you mean, included angle, and how to measure it.
How you're going to take that measurement. We have some simple tools for doing that. You know, kind of a plastic protractor.
Right.
But then you can also jump into the, we'll say, the digital world.
Yes, there are. I mean, there's some optical pieces that can look right there and define that crosshatch angle, and bang, there it is.
Put it right on your screen, tell you exactly what you want, and the neat thing is they're not expensive. They're not high dollar items. You're not talking thousands of dollars.
Right. Well, other thing too is that so crosshatch angle can be determined through the honing process. I know, like the old manual machines, you can adjust the belts and the pulleys and be able to get that speed and
feeds and speeds.
So you can create that angle. And of course, the newer CNC machines like the Rottler HXAY 45 and those 85Y, I should say, those machines, you can actually just punch the button and say, I want this number, and it just does it for you. So it's like super stupid simple.
The beauty of the modern computer.
Right, yeah.
But the older machines, you can get the correct angles, but you've got to be really careful. There are some, information out there that says, set it on a B pulley and a D pulley and this pulley, that pulley. The thing you've always got to remember is how hard you load it is going to slow the speed on the head.
Oh, that's true. Good point.
So that's going to change the angle. So even though you've set it the way the manufacturer or the machine said to do it, you still want to check that angle, because even though you did it right, it may have done it wrong.
Well, that's a great point. Great point. That's why it's important to trust but verify. So you need to be able to measure that, because it is a very important consideration. Now, back to you said the honing process, as how much load you're putting on it. Well, a lot of that also relates to the other part of this discussion, which is surface finish, because the crosshatch angle is just that. It's the angle. But what's holding the oil and that surface roughness, completely different.
Two different subjects. We're talking about ring rotation speeds, blow-by, movement up and down, and the ability to move oil up and down the bore. This is about oil retention. How do I keep that, as Lake eloquently says, that gasket, that seal. Oil is the seal. This is about how I move it around. This is about how I keep it.
Well, yeah, right oil, right place, right time, right amount. That's proper lubrication. This is how the oil gets there. This is what keeps it there. Because like you said, oil is the gasket. When you don't have enough oil, you will lose that gasket. Blow-by goes up, ring lubrication goes down, which means cylinder bore goes up, ring wear goes up, all bad things.
Pistons, we're blacked up in parts.
Just nothing's happy. So now with surface finish, we measure that with a profilometer.
Correct.
We have the tool to measure that, and it's going to tell you what those peaks and valleys are, and we've done lots of videos on that. So this video really isn't about digging into that. If you want to dig into surface finish, there's plenty of videos already on the Expo. There's plenty of videos on the Total Seal website if you want to go and watch that to get the real 101 on this. But the key thing is that understanding that this is different than crosshatch angle, because a lot of times people say, well, what's the crosshatch angle need to be? And it's like, well...
And how does this affect that?
Right. So talk about that a little bit. Explain how these two are related.
Well, they're, how do you say, they're distant cousins.
Yep.
You know, they are important, they are related, but again, surface finish is not going to change based on the crosshatch angle. We're looking at, you know, a very, very small area, very small amount of surface measurement where the data that we're gathering, we really don't see that change based on this angle. What changes with these angles are, one, ring rotation speed. Rings rotate on the engine. They're on the piston, I should say. They're always turning, unless it's a pinned ring like a two-stroke.
Right.
We've got to obviously stop that, can't have it go over a port. So this is going to help determine ring rotation speeds, but it's also going to affect blow-by and oil migration. As the angle becomes more vertical, more up and down, it's easier to move the oil to the top or to the bottom of the bore. You'll typically see steeper crosshatch angles, say a 60-degree included angle, in a long stroke engine, aircraft, locomotive, or an engine that has a hard time getting the oil back into the sump. Subaru, some of the flat engines are on a 60-degree crosshatch angle. It's easier to get that oil back down to the sump. But because it's easier for the oil to move, easier for the blow-by to move, easier for the air to move. So angle goes up, the oil movement is easier, blow-by goes up. So what do we want to do in the performance engine? Well, we don't want that blow-by.
No.
We want to flatten that angle out.
Correct.
But we can go too flat.
Yes, we've seen that before, right? Because now it becomes a scraper essentially, and you can't get enough oil migration to the bottom of the cylinder or the top of the cylinder, and you lose that oil retention, so you lose your gasket. Now the blow-by takes off again.
It's all out the window again. We get to a point where now my oil migration is not up and down, it's side to side.
Yes.
So we create that scraping damming effect. You can actually get into ring chatter because it's become so flat. Think about it like driving over a railroad track, bump, 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 bump.
Yeah.
So loads, unloads, loads, unloads, and we can get into that effect. So if you get into too flat of an angle, you can create a whole nother set of problems.
All right, so essentially what we're trying to say is these valley depths, which we know is important for holding oil, it really has no impact on this. I mean, you can have a 100 micro-inch valley or a 50 micro-inch valley. That has no effect on what that crosshatch angle is.
Absolutely. This is, again, we're back to the everything affects the other thing. We can't change this without changing that. We can have the absolute perfect surface finish and screw it up with the wrong crosshatch angles. We're too steep, too flat. You've got to find that, you know, that Goldilocks and the three bears just right. I've had quite a few customers that have done a lot of testing on where that sweet spot is. And what we find, generally speaking, is the old 45 degree does a pretty good job in most applications.
Yeah, it'll get you there.
It'll get you there. Big bore, short stroke, high RPM stuff, we'll flatten her down. You know, and I can't say how far they've gone, but to get it into the high 20s to mid 30s is not uncommon. Seems to work very, very well. Going the other direction. Big bore, or excuse me, long stroke, small bore. We're going back the other way because we can't get enough oil migration to the top. We see very dry bores, overheated parts. Simply, again, that lubrication. We're not there for the gasket or the ability to move the heat out of the cylinder.
There's a big thing about it today. It's so common to have very long stroke engines. I mean, some of these giant Pro Mod engines, think about, I mean, they're big bore, but they're also really long stroke. I mean, cylinders that are massively long. You can't run a narrow crosshatch angle with a cylinder that long because you just can't get enough oil migration up and down.
They don't like it.
You're trying to reduce blow-by, and you do tighten it up, and what happens is your blow-by goes way up because you just can't get enough oil where its speed needs to be that gasket. So I think that understanding that relationship between stroke and crosshatch angle is kind of a key thing that a lot of people just don't know.
They just, you know, they go with what the machine says. Again, we're back to, you know, kind of like honing's been for years. You know, here's my one and done. I do everything the same that comes through the shop. And
320 grit and send it.
Send it.
And well, that was okay with ductile moly rings, but it's not okay today with steel rings.
And soft blocks versus hard blocks. We've got to address all these things. So it's important to know what you're doing, what's the RPM range, length of the bore. We've got to help determine that crosshatch angle to go with that cylinder finish and just bring that package to the best that it can be.
Package?
It's a package.
Sounds like it might be ring seal soup. It's a combination. It's soup, not steak. It's not just this angle, it's not just that surface finish, it's not just this stroke, that oil viscosity. It's the combination of all of them coming together. That ring seal soup is what yields the performance, but ultimately you're looking for, because a higher performing engine typically means it's a longer lasting engine as well.
You look at the modern engine today, look at, Pro Stock, NASCAR, Supercar. It's the longevity that's coming out of these engines today compared to just 4 or 5 years ago. It's unbelievable.
Right.
It would just say, we're not selling as many rings to them.
Right. But they're not rebuilding those engines as often as you think they are. They last a lot longer. And again, better quality materials. You go from a ductile iron ring to a steel ring with the PVD coatings. Now that ring can last a long time if you get the rest of the soup dialed in.
Yep, that's it. You got to have that package, that suit. You get all this right, it's amazing how long it goes. I get the calls all the time. I got 100 passes on it. You think it needs to be re-ringed? Hey, I'm certainly taking it apart and I'm certainly looking at it, but I've got guys going 1,000 runs on drag car these days. Again, that's not helping my sales, but hey, it's the honest truth. We're here to tell you what it needs to be, help show you what it needs to be to get that longevity, to get that performance. This is what this is about. This is about education.
Well, like I said, my personal experience at Shavers with a little small block test engine, over 1,000 dyno pulls in 2 years on 0.7 millimeter steel rings, no loss of power. And we were doing power testing all the time, so we could see what was going on. There's just no degradation.
Yep.
But we had the whole package right. We had that soup, we had the right ring, we had the right surface finish, the right cross hatch angle. It all worked together, and the performance was unreal.
Yep.
And just the longevity was really what blew you away, because you couldn't have done that with the older 043 rings and all that. It just wouldn't have ever done it.
Never.
So getting that soup dialed in, that's the key. Hope you guys enjoyed the video. Hang around. We're here for more questions and answers.
Doesn't love Keith Jones. Oh my goodness, Keith Jones, what a great presentation. We're back live here at the Engine Performance Expo. Hopefully everybody's having a great day out there and enjoying all the content. We're going to talk about something that has been alluded to and touched on over the course of all 3 expos, and that is coatings, high performance coatings. We've got Brad and Gary in the house from Calico. Lake, I know you guys work together on various projects, and so it's going to be an alphabet soup of various coatings. Gentlemen, welcome. How are you?
Good, doing real good. Glad to be here. Thanks for inviting us.
Exactly. And so coatings, DLC, and all these different terms are thrown out there, and it seems like the coatings have been right in step with the performance and durability increases that we've seen in all these engines across all motorsports.
I think so. I mean, it's once you got to a certain point in motorsports, everybody started thinking about parasitic loads and making things, thinner oils, making things live longer and last longer. Of course, they got expensive, so they had to last longer. So coatings was just a natural evolution to come in. They were coming one way or the other.
And how do you find your way into that business industry and have that knowledge?
Well, in my case, I retired from the military and didn't have a job, so I had to get one.
There you go. So there it is. I need a job.
Well, I need a job.
The military has been using, these technology is kind of new, we'll call it still, maybe the last couple of decades in motorsports. It's new to the public because it wasn't around, but it's not new technology. It's been around for a long time.
Oh, absolutely. Absolutely.
And the thing to me is, this is back to tribology for the win, Joe. DLC coatings, PVD coatings, this process, this is tribology. Friction, wear, lubrication, and what we're doing here is that culmination of surface finish matters, right? It's not just about, hey, did I put this really great coating on the part? Well, what surface finish was under it? What's that process? So, Mark Conquest was here yesterday. We were talking about lifters. So here's one of the flat tappet lifters that's uncoated. And this is a DLC coated flat tappet. And like you said, alphabet soup, DLC stands for?
Diamond-like carbons.
Right, and it's a process. Explain the process of how we take this part and make it look like that. Because it looks cool, but the look isn't the key. It's that's on it and how it functions. So talk about that a little bit.
Well, DLCs is just one of the 100 plus coatings that we do. But DLC is done in a vacuum chamber, and it's an all chemical process. It's a process is chemical vapor deposition.
Okay.
And through chemical vapor deposition processes, you're able to create DLCs, diamond-like carbons. And there's a lot of different chemicals that go into creating different types of diamond-like carbons.
Right.
But that's kind of a generic name. And they're done in vacuum chambers, negative vacuums with and apply electricity. And then you put chemicals in. So carbon, for example, comes from a lot of places. The most common that most people know is acetylene with a cutting torch.
Right.
And everybody's been around it for a while. No, well, you cut the oxygen off, and all of a sudden you got this black soot coming out of the acetylene. Well, that black soot is carbon, which is a form of what we're talking about here. And obviously, you're going to put in an erasement. It's got to be much purer than that.
Right.
But you could, in fact, do a DLC with that carbon supply if that's the level of DLC that you want to create. And it's very, very complicated to do, but it's basically a gas in a chamber and a vacuum, and it's bombarded to the part, and it attracts it to the part with electricity.
And bonds, and creates
bonds.
a very hard, very low friction film. And that's the part we really like, is hard and low friction, right? Because it's got strength, and it's got durability and low friction. And I like reducing friction. That's always kind of fun. So, Brad, talk about some of the other things you said you do, not just DLCs. We see this giant bearing there, which the diesel guys and other people, industrial people will love that, because that's definitely not a small block Chevy main bearing. So what makes that bearing different?
Yeah, so Calico actually started with what we call a CT1 coating, which is a bearing coating.
Okay.
That's what we grew the company on. And then as we engine builders started throwing, more power, more fuel, government's taking out all the lubricants out of the fuel, so the engines are burning hotter, right? So there's a need for better performance.
Right.
So like you mentioned, the finish on the parts, the coatings that come after that. So we have over 100 different coatings that we supply on our thin films that we've been talking about, the DLC and the PVD, physical vapor deposition coatings. But we also do the thick films, so your engine bearing coating, and it's a dry film lubricant.
Right.
So
that's the key.
As you apply this coating, it increases your load carrying capacity, decreases the friction.
Right.
And it also has oil retention. So as that crankshaft,
these nice things.
Yes, and one of the good things is if you ever do lose oil supply, you have that split second longer to get to the kill switch.
Right.
So that way you don't destroy your crank. So
margin.
Correct.
It gives you margin.
Correct.
Right.
So, and then if something does happen, the coating actually has some embeddability. So it'll catch some of the trash and debris that's in the engine. So that's what we really built the company on. And we've just expanded so much with, the valve coatings, the chromium nitride, the DLC on the valves, piston rings, lifters, flat tappets, rollers. I mean, there's a need in almost everything. There's friction in an engine. So how do you get that friction out to free up more horsepower?
That's pretty much what Keith Thornton and Mark Cronquist have been saying yesterday and today. It's all about increasing efficiency, and you got to do that through reducing friction and surface finishing. And this is exactly where all this comes together, which is why it's so cool. And you see all these parts, the evolution of the parts. That as the parts get better, the coatings come into play. The surface finish comes into play, because that's what elevates the performance, is by adding that ability.
Well, at least with Calico, we typically get involved in projects, new projects, because of 5 basic reasons.
Okay.
You're having heat issues, you're having wear issues, you're having friction issues, which generates heat, you're having erosion issues, or you're having corrosion issues.
Right.
Those 5 problems are 99.9/10 of the problems that we solve.
Right.
And we're all racers.
Yes, sir.
The company was founded by a racer. He races today. His daughter races. Anybody knows anything about Calico? No, you see us around the track everywhere.
Oh yeah, he's a racer.
He's a racer. But industry is what drives a lot of it too. So a lot of these coatings weren't initially developed in the racing industry, but they came to the racing industry out of need to solve one of those 5 issues.
Right.
Exactly.
And that's why we reached out to you guys to, hey, let's work on some different coatings for piston rings, because steel rings, we need PVD
coatings or CVD coatings on piston rings in order to elevate that performance, which is why we like working with you guys to be able to come up with something new and different to continue to elevate things and make it better.
You were talking about surface finishes earlier. That's very extremely important. Not just with the thin films and the DLCs and the piston rings, but with everything that we do, even the bearing coating. And we have our own lab in house. We don't have we control all of our own finishing processes. We do it all in house so that we don't have to send anything out and get handled a lot. Because one thing's for sure, I always say you're not a good baseball player unless you can run all the bases.
Yeah.
You know?
Yeah.
So you can hit a home run, but if you don't run the bases, it's not a home run, right?
Yeah, you got to touch first.
So prepping the part correctly and getting through those steps and getting that right surface finish is extremely important. It's obviously the most important in a thin film coating, but it's just as important in a bearing coating as well.
Yeah. Just like paint jobs. Prep is everything. You can have the best paint in the whole world, best spray gun in the whole world, but if your prep job stinks, guess what? Your paint job's going to stink.
There it is, I can imagine. But at least now we know some of the secret sauce behind the scenes, and when Lake is throwing the alphabet soup at us, we know who he's talking about. Gentlemen, thank you very much. Appreciate it. Love what you do, and the parts are beautiful. Thank you so much. Lake, we're moving forward here at the Engine Performance Expo.
Exactly. A little more technology coming at us, so right down the road here in Johnson City, we need to go visit Jamie Abraham at Universal Tool to talk about some CNC tube benders. So stay tuned and watch the video. Hi there, and welcome back to the Engine Performance Expo. Again, I'm Lake Speed Jr., and today we got something really cool for you. You all know about CNCs, right? Computer numerical control. When we think about that in terms of lathes and the mills and the things you see in the background, we got something pretty special for you today. I'm here with my buddy and fellow University of Tennessee graduate, by the way, Jamie Abraham. We're here in Johnson City, Tennessee at Universal Tool Company. So Jamie, tell them a little bit about how you guys are using CNC technology, but you're using it to bend things.
That's correct. At Universal Tool Engineering, we manufacture, import, and distribute CNC tubing benders. These tubing benders can be used to bend any kind of tube or pipe, fuel lines, brake lines, and today specifically exhaust pipes.
Exactly. Headers, yeah, because the first time I was ever introduced to CNC tube bending was I was working at Melling Racing. It was for chassis. That was the whole thing. Is obviously you wanted the chassis to be consistent. That was always the big thing. I mean, for anybody who's watched any of the episodes of Engine Performance Expo in the past, you'll know that Doug Yates talked about how CNC head porting revolutionized the engine building business, because now it wasn't about, well, this guy had ground this one set of heads and it was the perfect set of heads, but you couldn't repeat it. So the repeatability got better. So with tube bending for chassis, that was a huge deal.
We can bend chassis as well. We can import the models from the computer to the tube bender. So each chassis, any tube, any muffler pipe, header will all be consistently the same over and over again.
See, that's really cool. So what you guys have been doing is applying this technology, like I said, from something as small as brake lines. You got a little bitty machine bending stuff. You got some pretty big machines that are bending exhaust pipes.
That's correct.
Because header technology is a huge piece. We talked about Engine Performance Expo. We've got lots on intakes, manifolds, head porting. That's all airflow into the engine. That air has to leave the engine. Yeah, me being a two-cycle guy, we do more tuning with the exhaust than we do anything else. So I'm all about getting down to this, just seeing how you can utilize this technology to, one, speed things up. Because it's one thing to be consistent, which is huge. You have to have consistency. But talk to us about how you can use this technology in order to speed the production of taking that idea and turning it into reality.
Yeah, so I mentioned earlier that we can take a computer file. So any of your CAD softwares,
Mastercam, or I guess that's
Mastercam, SolidWorks, AutoCAD, any of those. We can export a step file or an IGES file directly into the bender. We can bend that tube shape, that profile, and then we can measure it with a measuring arm, a laser measuring arm.
Okay.
And that has a closed loop correction on it that actually corrects the bender, so your second part looks exactly like what you have on your computer.
Oh, you're going to show us how that works, right? Because I think we all want to see that.
We're going to show you how that works today.
Okay, cool. So, all right. So you said you basically most time you begin with a CAD file.
That's correct.
But what if someone just happens to show up? Hey, I got this. Can you make me this?
Absolutely. We can take the laser measuring center, reverse engineer that tube, go over to the tube bender, and bend that tube from the sample.
So that lasering measuring center, that's not this thing right behind us,
That is this thing behind us, yes.
All right, cool. All right, so you got some guys who can put to work and show us some of this stuff?
Absolutely.
Let's make it happen.
Okay, so here we're going to bend up a part shape, a tube shape that's been predetermined, and we're going to take it over to the measuring center and measure it. We're going to show you the computer in the measuring center is going to compare it to the print data. You're going to see that the out of tolerance parts of it come up in red. We're going to send those corrections back to the bender. We're going to come bend the second one. We're going to go over there and take the second one and measure it, and you're going to see that all the tolerances come in green. That's a perfect part to the print. So what we have here is a non-contact arm with a laser probe, and Fred's going to measure the edge and then every straight section of the tube using a software called V-Tube Laser. It's taking thousands and thousands of points each time that little red dot hits that tube measurements. Now he's going to tell the computer to compare it to the print data. Now you can see the out of tolerance are in red, the intolerance are green. So now we're going to send those corrections to the bender. So it sends the adjustments. Now we're going to bend the second one and measure it. He's going to compare it to the print data. And you can see here, 100% of our points are in tolerance, and everything is 100% in the green for a perfect part to print. Okay, so previously we were showing you how to bend a tube, measure it, the measuring center, correct it, and then your second part's the perfect part. So now we're going to take it a step farther, and we're going to automate the whole bending process. So here we have an automated tube bending work cell. We have a bundle loader over here. We can put a whole bundle of tubes in. It separates it out, puts them in each ramp. The ramp escapes one tube at a time. It rotates the tube, finds the seam. If we don't find the seam, it bends differently if you're bending over the seam or across the seam. After we find the seam, we pick it up here and we put it in the bender. We bend it, and then the robot's going to offload the bender into a parts bin. Okay, here we have our 70 millimeter all electric tube bender. Other two machines we looked at earlier, we were running a single stack of tools on. Here we got 3 stacks of tools set up on this machine. The bottom stack is set up for bending. The center and top stack is set up for punching. We can use these stacks to punch or pierce into tubes for something like an oxygen sensor. Let's watch it run. Thanks for watching. We appreciate your time. More information on our product can be found on our website at universaltool.com. Thank you.
What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.